This is worksheet 4 capacitors. So this is section B. Question 7a. Explain what is meant by the capacitance of a capacitor and then define the farad, the unit of capacitance. So if I just write, there's no room here, so if I just write on a white sheet, so this is 7a, and capacitance then is the ability of a capacitor to store charge. Now there's no reason why you couldn't also explain this as capacitance being Q over V, the amount of charge stored per unit volt across a capacitor. So either of those two answers will get you your marks there. The second part, define a farad. So I'm going to do this in a different colour. So 1 farad, if you remember, if I write over here that C is equal to Q over V, and if you write that as 1 farad equals 1 coulomb over 1 volt, that's really what you're trying to explain there. 1 farad is 1 coulomb over 1 volt. But you need to put that in words a little bit better. So 1 farad is the capacitance of a capacitor which has the ability to store 1 coulomb of charge per unit volt. So it's the capacitance of a capacitor which can store 1 coulomb of charge per unit volt. It can store 1 coulomb of charge per unit volt. And there's your kind of working out there that's helping you to do that. You see that at the side there. Okay, we skipped part B because it was a description about a reed switch, and you don't have to do that anymore. So if we just relook at part C there, it says part C shows a circuit containing a capacitor of capacitance C, a resistor of resistance R, and a battery of EMF E and negligible internal resistance. When the switch is closed, then this is charged by the battery. When the switch is opened, so this is now disconnected, it then discharges through the resistor. The time constant of the circuit is given by tau is equal to C times R. By considering the units of the quantities involved in the equation for tau, confirm that the unit of the time constant is the second. So if I just scan in a wee bit there so you can see it a wee bit bigger. You've met this before already, and we'll just go through it again. We are just proving that the units of tau are equal to seconds. So this is part C, part 1. So we know that tau is equal to C times R. C is Q over V, R is V over I, and the V's go out. So you're then left with Q is equal to IT divided by I, the I's go out, and you're left with T, which has a unit of seconds, and you have proved your answer there. Q is equal to, sorry, tau has got the units of seconds, and that was part 1 of that question. So just to show you part 2, it says after charging the capacitor, switch S is opened at time t equals 0. I'll go out a wee bit there to see. At time tau, the potential difference, which is VAB between points A and B, is given by VAB equals 0.37 E. Deduce the values of VAB at times tau equals, T is equal to 2 tau, 3 tau, and 4 tau. So we have a wee quick look here. I'm just going to sketch out the graph which you have. And so your graph is always this exponential shape, and you know after 1 time constant's worth you've fallen to 37% of V naught. At time another tau you've fallen to 37% of 37%, so it's 0.37 times 0.37 V naught. and so on. So it's going to be 0.37 cubed once you get to, that's 2 tau and 3 tau. So it's just going to keep going like that. So you're always squaring, cubing and so on. So at t equals 2 tau, then V is going to be equal to 0.37 squared V naught. And that's going to come out then as, answer, 0.37 squared is 0.1369 V naught. So T is equal to 3 tau, then that's going to be 0.37 cubed V naught. And that's coming out there as 0.0506. I'm going to leave it as 0.05 V naught. And then if you have 4 tau, V equals 0.37 to the power 4 V naught. And that comes out as 0.018 or 19 V naught, and so on. Hence sketch a graph showing how VAB varies with T. I've preempted this a bit because I have it sketched already. Label the axes with values corresponding to the times tau, 2 tau, 3 tau, and I should have really kept going there to show you 4 tau. That's your time axis, and that's your potential difference axis, or your voltage axis. Okay. Part 3. A second capacitor, also of capacitance C, is now connected in series with the first as shown in figure 7.2. Find the new time constant Ts of the capacitor resistor circuit in times of tau. Describe quantitatively how the graph of VA versus T for the circuit of figure 7.2 would differ from the one you drew in your answer to C part 2. So if we just go back to this again, now you've got two capacitors. They're in series with each other. They are identical. So this is part 3.1. So your new capacitance is going to be, because they're in series with each other and they're identical, it's going to be half of one of them. So new capacitance is now C over 2. And therefore your new tau value, which they call TS, is going to be equal to C times R, but C this time is C over 2 times R, which is CR over 2, or it's tau of the first circuit divided by 2. So the new tau value is the original tau value divided by 2. Describe quantitatively how a graph of, so just to show you that graph, you can see there that there's your first graph there, which shows that whenever you have initial voltage of E, the graph fell like this. But whenever you have your new time constant, which is CR over 2, then it's going to fall in half the time. So it's going to have, by the time it gets to 37%, the time is going to be half of that. So you can see there's our original tau, and that's the 37% of our initial E value. But now that you've got your new time constant, which is CR over 2, then in half the time it's fallen to 37% of its initial value. And if you just show you down at the bottom there's where I've marked my tau values there, tau, 2 tau, 3 tau, and half of that is where we're having our 37% there. And then by the time 2 half-lives have passed, I shouldn't be saying half-lives, by the time 2 time constants have passed, we're down to another 37%, whereas over here we've only just got to our first 37% over here in our original circuit.